In this presentation, we go over a CFD model of flow characteristics around a low-speed aquatic propeller. This presentation was prepared by E.J. Dorian and Travis Gowan at the University of Utah Department of Mechanical Engineering. We investigate vortex wakes of low-speed aquatic propeller using SOLIDWORKS flow simulation at two Reynolds numbers of 781 and 3,851. This slide goes over the standard calculation for Reynolds number with the propeller. Once again, our experiments were performed at a Reynolds number of 781 and 3,851. In order to get a rotating region, we modeled just the propeller rather than the propeller and rudder that was modeled in the previous experiment. The mesh is biased towards the propeller, so there's more grid cells around the center of the propeller than there is further out in the free stream. Our boundary conditions are the inlet velocity according to the water channel speeds calculated during the first portion of this project, and a rotating no-slip condition with propeller speeds based on the water channel experiment again. We attempted to validate our CFD model with our experimental results from the drag force. The experimental data does not agree well with our experimental results, and that could be because our experimental data was very noisy and our propeller was very small, meaning that we don't really have reliable data on our propeller to compare to in the first place. We are relatively close and within an order of magnitude of what is expected.
This is a flow visualization at the Reynolds number of 3,851. The propeller speed in SOLIDWORKS was set to a rotation of 0.16 radians per second. On the left-hand side is the video from our experimental results in the water channel, and on the right-hand side is shown the streamlines for our SOLIDWORKS flow simulation. As you can see, the streamlines in the simulation tend towards the center of the propeller, as also seen in the water channel. This flow visualization shows the recirculation zone around the nose of the propeller. This is a visualization at the lower Reynolds number. You can see that the flow speed in the numerical simulation is reduced, but the streamlines still tend towards the center of the propeller. Again, this is a visualization of the recirculation in the lower Reynolds number case, which is still seen here. However, the recirculation is more tightly concentrated around the nose and is advected downstream less. Higher drag was seen in the simulation. This is likely due to transducer losses in the water channel from the torque moment on the rod and the amount of noise in the data. Recirculation, as said before, was seen in both the experimental and numerical case, but the standing recirculation in the wake at higher Reynolds number is likely due to advection momentum. Also, the experimental results are inconclusive, as stated before, and in order to get a better validation case, the water channel experiment should be rerun with a larger propeller to reduce the effect of noise on the data and improve surface roughness on the propellers to prevent dye from sticking to